Welcome to The Explainer. Today we are going on a really fascinating cosmic journey to uncover the actual physical mechanics behind our changing weather and the cycle of the seasons. We experience these changes every single year, the intense heat of summer, the bitter chill of winter, but the cosmic machinery driving the whole thing is honestly pretty misunderstood by most people. So we're going to break down the physics, look at the geometry of our planet, and give you a crystal clear picture of why the Earth behaves exactly the way it does. So let's just jump right in with a super common question. And honestly, it is the most intuitive assumption people make about the changing seasons. When you're standing outside feeling the intense heat of a July afternoon, it is completely natural to just think, wow, we must be physically closer to the sun right now. I mean, it makes logical sense, right? You stand closer to a campfire, you feel more heat. But as we're about to see, when it comes to planetary physics, our intuition is actually leading us totally astray here. Well, NASA's actual orbital data completely shatters that whole distance myth. Seriously, the numbers are pretty wild. Earth's orbit is a little bit elliptical, which means, yeah, our distance from the sun does change. The point where we are closest to the sun is called perihelion, and we actually hit that in January when we're about 91.4 million miles away. But the point where we're farthest, aphelion, that happens in July at 94.5 million miles away. Think about that for a second. During the Northern Hemisphere's absolute hottest, most scorching summer days, we are actually over 3 million miles further away from the sun than we are in the dead of winter. So, bottom line here, distance from the sun absolutely does not dictate our seasons.
The true culprit, the 23.5-degree tilt.
Okay, so if distance isn't the cause, what is? Well, the Earth doesn't sit straight up and down on its axis as it orbits the sun. It actually leans at an angle of exactly 23.5 degrees. How did that happen? Well, scientists believe that billions of years ago, back when the solar system was young and super chaotic, a massive planetary body named Theia literally smashed into Earth. That primordial collision completely knocked our planet off kilter. And, well, it just stayed that way. That ancient violent impact is quite literally the reason you and I experience seasons today. And here's the real kicker. As the Earth revolves around the sun, that 23.5-degree tilt stays absolutely constant. It is always pointing in the exact same direction out into space. Because of this permanent lean, as we make our yearly loop around the sun, one hemisphere is constantly leaning right into the solar rays, while the opposite hemisphere leans away. So in June, the North Pole is angled toward the sun. 6 months later, in December, we're on the totally opposite side of the sun, and the South Pole takes its turn leaning into the light. This tilt is absolutely the undisputed master switch for our global climate. Section 2. The physics of light. Unlocking the angle of incidence. This brings us to a really critical scientific concept, which is the angle of incidence. Imagine a line pointing straight up, totally perpendicular to the ground you're standing on. Now imagine a ray of sunlight coming down and hitting that exact same spot. The angle of incidence is just the geometric angle between that vertical line and the incoming ray of sunlight. Now, why does this actually matter? Because this specific geometric relationship dictates exactly how much solar energy the ground beneath your feet can actually absorb. It's kind of like shining a flashlight straight down at the floor versus shining it across the room at a really sharp angle. Let's look at summer first. Because your half of the Earth is tilted toward the sun appears very high up overhead. This creates a really small angle of incidence. The sunlight is hitting the ground almost dead on, concentrating all of its energy into a tight, small area. It's super intense. But in the winter, totally different story. Your hemisphere is tilted away, so the sun appears super low in the sky, creating a huge angle of incidence. The rays are coming in at a severe, shallow slant. Now remember, it is the exact same amount of sunlight, but now it's spread out over a much larger, stretched out area of the ground. That makes it far less concentrated, and as a result, way less warm. To really lock this concept in, let's look at this quote derived from a physics breakdown by educator London Jenks. He notes, "The sun always gives off the same amount of sunlight. What changes is how this is distributed or spread out." Basically, the sun's output isn't fluctuating at all. Our tilted perspective is what forces that totally constant energy to either concentrate like a magnifying glass in the summer or diffuse really weakly across the landscape in the winter. Section 3. The yearly orbit. Solstices and equinoxes. So here is the orbital timeline of our planet. As Earth travels, there are 4 precise astronomical milestones that are defined entirely by our tilt relative to the sun. Around March 20th and September 22nd, we hit the equinoxes. Then, around June 20th and December 21st, we hit the solstices. Now, these aren't just arbitrary dates on a calendar. They are very distinct physical positions in space that dictate the absolute extremes and the midpoints of our entire seasonal cycle. Let's start with the equinoxes. During the spring and fall equinoxes, the Earth's axis is leaning neither toward nor away from the sun. The sun's path is perfectly aligned with the Earth's equator, and the results, perfect global balance. For just a brief moment, practically everywhere on Earth experiences roughly 12 hours of daylight and 12 hours of darkness. It's this beautiful transition point, a moment of pure cosmic equilibrium, right before the tilt begins to favor one hemisphere over the other. And then, of course, we have the extremes. The solstices. The summer solstice marks the exact day when a hemisphere reaches its absolute maximum tilt toward the sun. The sun gets to its highest possible point in the sky, giving us the smallest angle of incidence, the most concentrated heat, and the absolute longest day of the year. Conversely, the winter solstice is our maximum tilt away from the sun. The sun barely even scrapes above the horizon, the solar energy is completely diffused, and we end up experiencing the shortest day of the year.
Section 4. Daylight Extremes. How latitude changes your day.
First, let's establish a quick baseline. It takes about 23.9 hours for the Earth to complete one full rotation on its axis. We usually just round this up to 24 hours. But while that rotation time is totally fixed, the actual amount of that time you spend bathing in sunlight versus sitting in the dark depends entirely on how far north or south you live from the equator. So, if we break down the data for the summer solstice in the northern hemisphere, it's pretty wild. If you live right at the equator, at 0 degrees latitude, you still get a perfectly balanced 12 hours of daylight. But, travel up to the mid-latitudes, say New York at 40 degrees north, and suddenly you're getting about 15 hours of daylight. Now let's go all the way to the extreme, the North Pole at 90 degrees north. Because the very top of the Earth is tilted entirely into the sun's rays, they get a full 24 hours of daylight. It's the exact same day on the exact same planet, but you get radically different experiences based totally on your latitude. This extreme polar effect is known as the midnight sun. Because the Earth's axis is tilted at roughly 23.5 degrees, the latitudes at the very top and bottom of our planet actually get locked into periods where the sun simply never sets. The Earth is spinning, sure, but the tilt actually prevents the pole from ever rotating into the Earth's own shadow. So for months at a time, the sun literally just traces a circle in the sky, never once dropping below the horizon. Now, let's contrast that freezing, highly slanted light of the poles with what happens down in the tropics. Between the Tropic of Cancer and the Tropic of Capricorn, the sun's path passes directly, vertically overhead at least once a year. The angle of incidence is practically 0. That means the sunlight is incredibly intense and direct. And because the sun is always relatively high in the sky down there, regardless of what season it is, the tropics experience consistently warm temperatures year-round. They completely bypass the massive extreme temperature swings felt by the rest of the planet. Section 5. Putting it all together, the mechanics of our climate. All right, let's do a quick recap of our core takeaways today. Number 1, banish that distance myth for good. Being closer or farther from the sun absolutely does not cause our seasons. Number 2, Earth's 23.5-degree axial tilt is the true absolute driver of our changing climate. Number 3, this tilt changes the angle of incidence, dictating whether sunlight hits us directly to concentrate heat or at a massive slant to diffuse it. Number 4, our solstices and equinoxes are the precise geometric milestones of this amazing yearly orbital dance. And finally, your latitude dictates exactly how intensely you will experience these wild extremes of daylight and temperature. As we wrap up, I really want to leave you with a kind of wild what-if to chew on. Our entire biosphere, our agriculture, and honestly all of human civilization are perfectly fine-tuned to this extremely specific 23.5-degree tilt. If some cosmic event were to shift our axis even just a few degrees, how drastically do you think our seasons would change? The delicate, incredibly precise balance that makes life as we know it possible is quite literally hanging on a tilt. Thanks so much for joining me on this explainer. Keep looking up and stay curious.